So here's a brief review of oxidation numbers. So if we take a look, those are the rules. You've got to know the rules. Usually I actually have rule number 9 and 8 switched, but I don't think it'll be a problem because it says always. So if we take a look, all of this beginning part is basically the same rule. Everything has to add up to its state charge. So anything that is like, for example, if I have zinc metal, its state charge is 0. So the oxidation number for that zinc would be 0. If I have that zinc metal and it is mixed with, it's in the ionic compound zinc sulfate, well, what is the charge of sulfate? -2. So that means that that zinc must have what oxidation number? +2. If we were then to break down the SO4, the sulfate ion, we now need to actually go down to other rules. But the sum of these guys right here must equal that -2. So group 1A won't help us here. Group 2A won't help us here. Hydrogen will not help us here. Oxygen will help us here. Because oxygen is usually -2. The fact that we made it all the way down to this level of rule, that means this rule is going to be true. Even though oxygen is usually -2, we have no other rule that subsidizes, like that sits there and says, okay, no, this could not be true. What if we had H2O? Well, what rule was before this? Hydrogen is +1. So that means that this rule would not necessarily be true, right? Because this rule substituted it. If we have H2O2, hydrogen is +1. Since this has to add up to 0, that makes oxygen -1. So we had no other rule come into play until we got down to oxygen is -2. So that makes oxygen -2. That makes the total charge of the oxygen in that thing -8. We don't have any rule for sulfur. So that means we have X plus -8 equals -2. What is sulfur's oxidation number then? 6. You guys know how chemistry loves to feed back on itself. This was designed for a lot of the things that I've already taught you. For example, finding the charges for multivalent cations, like iron 3 oxide versus iron 2 oxide. This was something that chemists created. The chemicals don't know they do this. This is something that chemists created to basically classify what they're doing. You can actually have fractions of oxidation numbers. It doesn't come up very much, but you could have it. Just keep that in mind. This is a system that was created. So if we take a look, assign oxidation numbers to these. This will be the assignment for tonight. I'll post the answers up tomorrow at some point. So if something is what we call oxidized, that means it loses electrons. If something is reduced, that means it gains electrons. There are 2 of these things that people use. The most common ones, so if you're going with another tutor or whatnot, they may say Leo goes grr. What is a Leo? Aren't you a Leo? No. What is a Leo? Lion. Did I hear somebody say tiger? That's amazing. I thought I heard somebody say tiger. Well, it's amazing. Leo goes grr. So basically what they're doing is they're making some, are these mnemonic devices? Is that the title of these? Yeah. Loss of electrons is oxidation. Gain of electrons is reduction. The one I always remembered as a kid was oil rig. So oxidation is a loss of electrons, reduction is a gain. But why is that tricky? Because if you lose electrons, your oxidation number will go, you're losing negatives, so you become more positive. And if you're gaining electrons, your oxidation number will go down. And basically that's what reduction, that term reduction is about, that oxidation number going down. You can see why this might be misconstrued by people. It's because they're like, but reduction is gain. But you have to remember the particle that you're gaining. Now, apparently they don't use this agent thing in the AP exam much anymore, but oxidizing agent is the thing that does the oxidizing, right? Just as, for example, if I said the cleaning agent is the thing that does the cleaning. The reducing agent is the thing that does the reducing. So here's the cool thing. An element in the reducing agent is actually oxidized, and an element that's in the oxidizing agent is actually reduced. But this makes sense if we think about what happens to soapy dishwater by the end of the dishwashing cycle. It becomes what? Dirty, but it did what? It did the cleaning, right? If you use these little things, maybe they'll help you. So oxidation reduction reactions includes all single replacement reactions. But this is basically, I think maybe I want to show you this. Yeah. Anybody have a penny dated before 1983? So let's take a look at this. And these ex-chemistry kids, they left this table a mess. Hopefully we can get it to the point where you guys can see it enough. Noah. He's my monk of this year. Dang it. I can never get a good response at you. You used to be more responsive, didn't you? Did you chill out over the first period? Okay, that's true. I never had that period 9. Which I will tell you this: my period 9 is the best period I think I've ever had. Period 9. Sorry, those of you old period 9ers, but they are totally upset because my period 5, 6 is much cooler than them. Period 5, 6 was like my 10, right? But did period 10 have the best grades? I think period 4, 5. Yeah. Are you serious? Yeah. Usually period 10 wipes out the competition. Yeah, that's exactly what I think I told them too, isn't it?
I remember Macy Miller was not in my class period, and we had a
She would
test
come
that
in
day.
sometimes.
She came in sometimes, and she took a picture of my stand from. What? Like 3 periods later, after I shot on video. Oh.
He was just telling us this funny story.
She's like, hey, Dylan, do you remember what you put for number like 37? I was like, yeah, I don't know. She's like, you put B. I was like, she's like, here's your stand.
That was wrong, John. Was it right or wrong? That's funny that she did that. Huh. Right? If you didn't notice it, how the heck was I supposed to? Your skin, John. How much did she give you for it? Kind of blame, right? All right, so this is copper 2 sulfate solution. How might you know that this is probably a copper solution? Right? Blue. What are some other common colors for copper salts? Pretty nice. Statue of Liberty. This is zinc sulfate solution. One of the reasons why we don't eat in the laboratory. Pretty poisonous. Right. One of the bad things about biting your fingernails as a chemist. So let's take a look here. I've got a solution of zinc sulfate and a solution of copper 2 sulfate. Yeah, I need a penny. Did we find one? Thompson 1983. Anybody?
Wait, why does that have to be from before 1980? Oh.
Hey, look at this. Look at me. What's the problem though? Yeah, there has to be, right? Coating on the outside. Why? Oxidation. Take that coating off the acetic acid.
Ooh, I have a 1981.
Oh. Here, let's take it off. I forgot I had this acetic acid. What's that? What's that mean? Oh, spring break joke?
Yeah,
Got her. Funny. I forgot my toothbrush on my pillow. That was the girl whenever we got down to Florida for spring break. Martha Rustler goes, I forgot my toothbrush on my pillow. I thought it was hysterical. All right, so I'm going to clean that off. While that's getting cleaned off, I have a piece of zinc right here. I'm going to drop that into the copper 2 sulfate solution. And then we're going to take a look at this second, and then we're going to take a look at what it does to the pinning. Now, if you have your activity series memorized, this would be pretty easy, right? So we can take a look at that old looking penny is now what? Nice and coppery. Cool. So now we're going to drop that guy into here. If we know the activity series well, we know that copper and zinc are both on that activity series, right? One has to be above the other one. It's more active, right? So only one of these reactions is going to occur. Anybody have an idea of which one? Zinc will react. Why did you guess that? Oh, you have some type of thing there for it? You have some type of thing there for it? Are you going by electronegativity or something? Might be able to. I never thought about it that way. The way I think about it is which of these metals have, which of these metals was kind of used first in the world of like for monetary coins or for copper, right? Why would copper be used for instead of zinc to make coins? Because it doesn't do what much? React. So who would we expect to be on the bottom of this list of activity series? The least reactive, which would be platinum, gold, silver, right? These are not very reactive things because you can actually mine for gold, right? That means that gold is not very reactive. Well, this unit is going to show us exactly why this activity series exists the way it does. We're going to look at what's called the reduction potentials or the oxidation potentials of things. That will give us an idea of how they react. If we take a look at this piece of zinc, instead of being shiny silver like it was, we can take a look and we can see that it is now, I don't know if you guys can see that on there, but it is now brown and blackish because it has been replaced, the outer coating of that zinc has been replaced by copper. And if we were to wash that off, then we would keep it in there, and it would happen again and again and again, right? And then we could have a collection of copper at the bottom. But our zinc mask just went up in my eye. Our zinc penny. Come here, you. All right. Our zinc penny, I'm sorry, our copper penny is not have any coating on it at all. Copper penny. Ugh. But there we go. So science in action. Questions on that? Do you guys have a copy of an activity series? Did I give you guys the old periodic table as well as the one that they will let you use for AP?
I know I have it, but.
The good thing for you guys is you guys have access to the internet mostly, right? All right. Get that. What kind of pen is that? You got Noah's pen? I think I should hold it ransom until he cleans up the messes he makes.
No.
You know how good I am at names, right? Noah Hansen? Is that a name? I think it starts with an H. You know him? He might be on Quizbo. It's different colors of blue. What if they're like red, green colorblind? So this is how they take notes. Is that possible?
Light blue. I don't think it would matter. Even lighter blue?
That might be like somebody's special pen or something, right? I don't know.
They haven't used it yet. All three of the little things have like the tip of
Oh my God. How sad is that? Like that's like you getting a new puppy and it like darting in the road immediately or something. That is like you lost it. You lost it before you got to have any fun with it. Yeah, we lived next to a highway. Yeah, it was not common to have to jump off the bus and grab the shovel. Whew. We didn't have really good names for our cats. It was baby cat 2, fat cat. Yeah, we loved them and everything. We just they were only like in your life for a short period of time. Never lost a dog to the road. Bus driver almost ran over our dog once as he's dropping me off because there they would drop you off right at your house whenever you live on a highway like this. And the dog comes running out to bark at me or whatever. And this is probably like second day of school at a brand new school in the country or whatnot. And because we were from Cincinnati originally. And the bus driver like opens the door. Dog ain't gonna last long like that or whatever. Lets me off and then closes the door. It was ridiculous. The dog lived, it didn't die from the road. I think it actually made it till after I was in college. Oh, yeah. The only time that dog liked me was when I was sleeping. I have no clue. All right, where are we at? So let me pop up the activation series real quick here. Are we back on? Okay. So here's the activation or activity series. Very small and not very clear. This is the problem with a digital camera like this. An actual regular camera would be able to pick that up. So I'm going to read them, but I think that hopefully maybe you can see that is magnesium, aluminum. Down here we have iron, there's chromium, nickel, cadmium, tin, lead, hydrogen. The major thing about this is recall that these first and second, the alkali and the alkaline earth metals, a lot of them can replace hydrogen and water. Now magnesium cannot, but a lot of them can. Now, all of these metals right here can replace hydrogen in an acid only. You can see that the last one there is lead. right before hydrogen. This is a major reason why they took out lead piping and stuff like that, because if the water was acidic at all, then that would leach lead into the water supply. And if you were drinking that and you had like, your brain wasn't fully developed or whatnot, that could cause some very specific brain problems. Right? What's that? It's possible, yeah. I'm not sure on that. Fortunately, I don't have it, but this is it's the whole like we said, the eating paint chips and stuff like that. Lead actually has a very sweet flavor. So I mean, lead also makes some amazing precipitates that are like beautiful colors, especially for the 50s and 60s, like yellows and browns and stuff that you see like all the suits and back from footage from that day, right? So people would paint their baby room in this beautiful sun yellow color, only to find out that years later, as it cracked paint, the kid was eating it and then developed mental issues. All right, so oxidation, loss of electrons, we said it, reduction gain, and there's the oxidation reducing agent. So, and I believe that this might be as far as I wanted to get today. Yep, all right, cool. So this is the second part of the assignment. Assign oxidation numbers to the following. Tell what's oxidized reduced, circle the oxidizing agent, and underline the reducing agent. If it is not an oxidation reduction, write Na. So we know that this is an element. So what is its oxidation number? 0. And this is group 1A, so it is +1. And this is an element, so it is 0. And this is paired up with sodium, which has to be +1, so this is -1. Notice when it comes to oxidation numbers, our coefficients do not matter, because we get to the answer, say, okay, it's 2 and -2, but we don't even have to think about it because it fixes itself. Sodium went from 0 to plus, and chlorine went from 0 to minus. If you have this all figured out, I suggest, you know, I do not like to think very much. So what do? I look for the one that is reduced. The one that went from 0 to -1 is reduced because it's gone down. That means that chlorine has been what? Reduced. And that means that sodium has been oxidized. Now that I have that figured out, I can actually start applying my knowledge and thinking. Since this was reduced, reduction is gain. Chlorine stole electrons from sodium. Stole is a strong word. They were more attracted, however you want to look at it chemistry-wise, but give me here, what's that? Yeah, Mr. Steal your electrons. So if we take a look, chlorine takes the electrons, giving it a negative charge because electrons are negative. Sodium has lost electrons, giving it a positive charge, and it is oxidized. If chlorine was reduced, that makes it the oxidizing agent. And that means sodium is the reducing agent. You cannot have an oxidation unless you have a reduction, and you cannot have a reduction unless you have an oxidation. That would break the law of what? Conservation of mass and energy. The law of physics. There's one law to rule them all, right? Yes. Yeah. In reality, if you don't like that, you can just write it out to the side. Yeah, since chlorine was reduced, that makes it the oxidizing agent. And since sodium was oxidized, that makes it the reducing agent. But it was just a way to get people to assimilate the information in their mind, right? That's it. That's what the first part of this is to get that down. What we could do then is we could break this into what we call half reactions. So what happened? This was oxidized, so it lost electrons. So that means that over here, sodium is separated from the electron. And here we have chlorine. Now, does this match for mass and charge? The top one here? We have a charge of 0 on the reactant side. We have a plus and a minus on the product side. So that becomes 0. So it matches for charge. Does it match for mass? Sodium and sodium? Yeah. Bottom one here, we have 2 Cls. So what would we need over here? 2. And then that also means that each one of these had to gain 1 electron. Since we have a 2 negative here, that means we need what in front of the electrons here? 2. So now does the top and bottom match? Because one had to lose the same amount that the other gained? No. So what do I need to do to everything in the top? Multiply it by 2. Right? So let me ask you this then. The top reaction would be called the oxidation reaction or the reduction reaction? Oxidation, and this is the reduction. So this would be called the oxidation half reaction. This would be called the reduction half reaction. If we take a, oh my God, I didn't number these pages. If you haven't printed them out yet, I will number them. Otherwise, you can write numbers down on the bottom. This is from the back. I can't believe I made that mistake. No. So this is on, it's like the back 2 pages. I tried to put it on the back as far as I could. And my mind was to, and I wasn't smart enough, I probably fixed it because it didn't make sense to me after all that stuff yesterday. My mind was to put a blank page at the end so you could pull off the review questions, but I did not do that. If you want to go in and doctor it before you do that, it makes it a little easier. I'll probably go do that myself. So if we're looking at this, here is one of the reactions. Na plus E yields NaS, negative 271. And what's the difference about this? What can you tell me about it? It's just 1, not 2. That's good. What else? Yeah, so it's actually forming a solid. Yep. So what does that mean? How is this different than what we have? Well, let's take a better look. How is that one different? Okay, good terms. It's flipped, right? It's flipped. Let's go back then. Since it's flipped, take a look at the top of this. This says this is standard reduction potentials in aqueous solution at 25. So these are standard reduction potentials. In our case, that was actually not reduced, it was oxidized. So all we would have to do to make this an actual oxidized potential is we flip it. What do you think happens when we flip this reaction though? You flip the sign. It's the same thing as like Hess's law and all that other stuff, right? So this is the reduction potential. If we wanted the oxidation potential, it would be instead of negative 2.71, it would be 2.71. Can anybody find our chlorine on there? Up, all the way up here. Look at that. Chlorine has a reduction potential of 1.36. And it is in the correct form, right? Let me ask you this. If I said that you had a potential of 1.36, and I said that somebody else had a potential of, where is it? Dang it, of negative 2.71. Which one do you think, in my regards, I think has the more potential? The positive one, right? The positive one. So that's what we're looking at here. The fact that chlorine has a higher reduction potential than sodium, when these two things get together in nature, which one's more likely to occur? Well, the chlorine is more likely to be reduced. Well, what does that mean then? Well, that means that the sodium, it doesn't have the potential to be reduced if it's with chlorine, right? So what does the sodium have to do? It has to be oxidized, right? And one thing is, if we look at its oxidation potential, it's kind of high, isn't it? Yeah. So if we put these two things together, then that's the course of action that's likely to occur. What's the only way we can make it not occur? Yeah, possibly have something else in there, right? That's got a higher potential to do one or the other. And that's going to bring us to the end of it. And we will see tomorrow that even if something goes one way because of chemistry, we've got ways to make it go the opposite. Well, that's all I got for today, guys. Scott, please, as soon as you can, after lunch or whatever is fine. I'll just use period 10 to make sure I submit all that correctly. Otherwise, if you have questions, by all means, stick around on the Zoom and have a good day.